In today's experiment, we shall see the stability of a Teeter toy-like structure. In this type of structure, two identical weights connected through an elbow is balanced through a pivot. In the schematic, we can see two identical masses are connected to a pivotal rod at a distance small l. The pivotal rod in vertical position has got length capital L. Masses M make an angle alpha with the vertical. Now let us try to see that what is going to be the potential energy of the structure when it is tilted to an angle theta. So now in this case, what we see is that this pivotal rod is making an angle theta with the vertical, and the mass on the left hand side that will be making an angle alpha plus theta with the vertical. On the other hand, mass on right hand side will be making an angle alpha minus theta with the vertical. We want to evaluate the potential energy of the structure. So for that, let us take the zero of the gravitational potential energy at the pivot point. So we require the height of the mass with respect to our reference point. For the left side mass, this height is going to be L cos theta minus L cos alpha plus theta. On the other hand, for the right hand side mass, this length is going to be L cos theta minus L cos alpha minus theta. So our potential energy expression is going to be mg for this mass L cos theta minus L cos alpha plus theta, and for this mass we have L cos theta minus L cos alpha minus theta. Cos alpha plus theta we can evaluate in terms of cos alpha cos theta minus sin alpha sin theta, and we can simplify this expression and it will turn out to be 2 mg cos theta multiplied with capital L minus L cos alpha. So this is going to be our expression for potential energy. For the case of equilibrium, du by d theta should be 0. So in potential energy expression, we see that only cos theta has theta dependence. When we differentiate, this becomes minus 2 mg sin theta L minus L cos alpha. This has to be 0. So that gives us a condition that when sin theta is equal to 0 or theta is equal to 0, we might get a case of equilibrium. For stability, we also see that when we take the second derivative of the potential energy at theta is equal to 0, and if it is positive, then we have a stable condition. So when we take second derivative, sin theta will become cos theta, other terms will remain constant, and at theta is equal to 0, cos 0 is going to be 1. So second derivative of potential energy at theta is equal to 0 turns out to be minus 2 mg L capital L minus L cos alpha, and this has to be positive. This can be positive if capital L is less than L cos alpha. That means center of mass must be the below the pivot point. If this is the case, then we will be having a configuration where we have a stable structure. For our experiments, we have taken two cricket bats and we have connected them through a PVC elbow, and we have used one stump, and its pointed side is going to act as a pivot for our experiment. So we have placed in this configuration. Now what we see is that when we rotate this whole structure, it rotates easily. There is no toppling or no falling off of our weight. We also tilt it to certain directions, and then you can see that it comes back to its equilibrium position. It is not falling over. When we place this structure at the pivot point, it simply stays there. So what we can see is that indeed we have a stable configuration, and definitely in our this arrangement the center of mass is below the pivot point. So indeed we have a stable configuration.